All right, so let's take a look at an example where it might be useful to square a function in order to find the derivative, okay, or find the maxima or minima points. So an animal enclosure is a right-angled triangle with one side being a drain. Okay, so here's a drain. The farmer that owns this animal enclosure has 300 meters of fencing available for the other two sides. Segment AB and segment AC. Notice this notation for the segment is slightly different from what you may have seen in geometry because this is not the American system, but that's fine, okay? So I have a drain on one side, I have AB on one side, I have BC. These two sides are going to be enclosed with 300 meters of fencing. All right? So the question is, if AB is x meters, show that AC is this expression here. And then part B says, find the maximum possible area of the triangular enclosure. Okay, so I need to find the maximum possible area, so that's probably going to mean I'm going to need to find the derivative of this area and relate it somehow to a variable. My independent variable in this case is probably going to be x. Okay? So AB has been given to us as x. Let's draw another diagram that has that information on there. Okay? So here's x. Okay, if this is x, since I'm using 300 meters, this plus this would be 300, so this must be 300 minus x. Okay, and I know it's a right triangle because the problem told us it was a right-angled triangle, and so we can use Pythagoras' theorem to create a relationship. Okay, we can create a relationship because what we're asked to find is AC. Okay, show that AC is this expression. So I need to relate AC with x, and I can do that using Pythagoras' theorem. So by Pythagoras' theorem, I do x squared plus AC squared is 300 minus x quantity squared, and I isolate the AC and I end up with this expression. So I've shown that this is how AC is determined. Now, find the maximum possible area of the triangular enclosure. So I'm probably going to need to find the area formula first, right? And since it's a right triangle, it's just going to be A equals half base times height. Okay, where the base is going to be probably AC or x, okay, and the height would be the other. It would either be x or AC. Now, I want to be once I find my expression. Remember, we want to start thinking about the domain to make our life a little bit easier later on when we're solving. So the way we find the domain is we look under the square root. Okay, that's got to be less than 300. Okay, because if I set this greater than 0, I'm going to get x is greater than 300, and also x must be positive because it's a distance, right? So this is my domain. Now, if I were to derive this, since I'm looking for the derivative, right? So this is sort of like step 2. I've built my function. Now I need to find the derivative and then set it equal to 0 to find my zeros. If I were to find the derivative of this, that would be really messy, okay? Because I have a square root in here. I would use the power rule, and I would just get sort of an ugly function, and it'd be difficult for me to find the zeros of that, okay? So we're going to use our technique here of squaring the original function and then finding the zeros of that function. Okay, and so once we square it, we end up with a of x quantity squared is x squared over 4, and the square root disappears, times 90,000 minus 6,000x. This simplifies, okay, if I were to simplify this, I get this expression, and so now I can find the zeros of this a lot easier than I would be able to with my original function. Okay, so if I find my zeros, I can factor that, or sorry, I can derive that. So once I derive that, then I end up with 45,000x minus 450x squared. Okay, so I need to find the zeros of this. I can factor that. I end up with 450x times the quantity 100 minus x. And then I use a sign diagram, or I guess you could check concavity once you find the zeros. But in this case, I'm just going to use the sign diagram. So I have from 0 to 300 is my restricted domain. And since my critical point here, or my 0, is occurring at 100 or x equals 0, but 0 is not a possible answer. So I just look around 100. Okay, I plug in a number that's less than 100. Let's say 1. That's going to be positive. That's going to be positive. So that's positive. I plug in a number between 100 and 300. Let's say 200. Okay, that would be positive, and that would be negative, so we have negative there. And so therefore we can say there's a local max occurring on f of x, quantity squared. So that's kind of something that you shouldn't forget there. This is going to be the maximum on my squared function right here, of this function. But x equals 100 will tell me still the local maximum on my f of x, on this function. Okay, so a of x squared has a max at x equals 100, and therefore a of x also has a max at x equals 100. And now I can just, okay, so I think the question asked me to find the maximum area. So I need to find the value of a at that value of x. So I plug in x equals 100 into my function, and I end up with 8,660 meters squared. And that's the area that's the maximum possible area in this case. All right?